Today, we want to build up more surfaces in R3. And we're going to do it in a similar fashion to the way we built up the linear function yesterday. We want to remind ourselves of some forms in R2 and then use that to expand to R3, figure out what's going on in 3 dimensions. Yesterday, we talked about linear functions in 3 variables. And the construction was the same as a linear function in 2 variables. Start the z value at z naught. And here's our slope in the x direction. And then we have a slope in the y direction. So we just have 2 different slopes. So m is going to be the dz, the delta z over delta x. And the n will be delta z over delta y. So we have multiple slopes going around. We should give them different names, more than just m and n. So that coefficient of the x is how much z changes when x increases by 1. And the coefficient of y will be how much z increases when y increases by 1. So this linear function in 3 variables is going to give us a plane in R3. One of the points on the plane is x naught, y naught, and z naught. With a slope of m in the x direction and a slope of n in the y direction. So at this point, we have a little bit more information that we can apply to the discussion where we're trying to take the calculus thinking and apply it to functions of 3 variables. Because now we've seen what a linear function looks like in 3 variables. This is important because if we go back to those two questions of calculus, what's the slope of the line tangent to a curve at a point? And what's the area under a curve and above an interval? We have now found out what linear functions look like in R3. Linear functions will produce planes in R3. This makes sense. The whole thing with linear functions is that linear functions are flat. This is why linear algebra is such an easy class. It's like linear algebra. Everything is flat. Everything is flat. That means it's predictable. This is our natural mode of thinking. Our natural default mode of thinking is to think linearly. For example, if I'm selling a car and my price is $5,000, then you might come in at $4,000 as an offer. And maybe we suggest to split the difference. That's thinking linearly. That's just drawing a line between mine and yours and meeting in the middle at 4,500. I forgot what I had said. I hope that's the middle of what the 2 numbers I had said. I said those numbers like a whole minute ago, so who knows what I said back then. I was younger. I said lots of crazy things. That's our default mode of thinking. When you're back in Calc 2, when you're finding area under a curve, you had an overestimate and an underestimate. What did you do? You averaged them. You drew a line connecting the 2. It's your default mode of thinking. That's why linear algebra is so simple. Everything is flat. That's our natural way of thinking. We start off with the flat plane. That's z equals 0. Then we move it to a point, x naught, y naught, z naught. So x naught, y naught, z naught. And then we angle a slope in the x direction, and then we angle it in the y direction. And there we have a plane. It doesn't change its shape just by moving it around, and multiplying by constants. Not going to change the shape doing that. So if we think back to Calc 1, where we started learning about slopes of tangent lines, the tangent line is the best linear approximation of a curve at a point. It's the best linear approximation of a curve at a point. And we said the slope is dz dx, and we called that the derivative of z with respect to x. And then we produced a tangent line. We'd say that the tangent line would be z equals f at x naught plus f prime at x naught times x minus x naught. And that's the equation of our tangent line. Point and slope that match the function. What have we added by making our linear functions look like this? Just another term that looks the same. Moreover, we're still using slope language. M is dz over dx. In the case of a tangent line, that was the derivative. There's only one variable running around, so we got to just say the derivative. But now I've got a dz dx and a dz dy. Slopes are rates of change. I've got a rate of change in the x direction, and I've got a rate of change in the y direction. Let's just install some calculus language on that. I've got a derivative in the x direction, and I've got a derivative in the y direction. I've just got these two derivatives standing in for the slopes. It's going to have to be this way, because when we make a tangent to a curve at a point, we're creating the best linear approximation of that curve. So the tangent line is a linear approximation, a best linear approximation of a curve at a point. Tangent line is a linear approximation of a curve at a point. If we upgrade our curve to a surface, our best linear approximation is no longer going to be a line. It's going to be a plane. Tangent lines are found with derivatives, so these tangent planes are going to be found with derivatives as well. Any questions? How's everybody okay? We're just upgrading our old stuff. The thinking is still the same. We're just adapting it. Just evolving our thinking. which is all we ever want to do. I mean, that's the whole point of this entire exercise, not Calc 3, not your particular program. This whole point of just sitting in a room talking about ideas. We're just trying to get different perspectives. You know what I mean? A lot of criticisms that get leveled at schools, a lot that are valid, some that are a little bit iffy, some that are just edgelords trying to be edgy. But even teachers walk around with the idea that they want to teach people how to think. And then if you want to be edgy, it's like, oh, they're just trying to tell you what to think. I don't want either of those things. First of all, I am 100% incapable of teaching you how to think. I know how your mind works. It works differently than mine. It works differently than everybody else's. That's why we find it so amazing when our best friend and ourselves think about something the same way. It's like, oh, you know, blah, blah, blah. They're like, oh, hell yeah. Then you're like, oh, did we just become best friends? It's like, well, I think so. Because that doesn't happen very often. I can't teach you how to think. I don't know how your mind works. I haven't been observing you for the last 20 years of your life to see how it's going. Granted, those first couple of years, your brain was just like, oh man, there's so much to work out. I'm not going to remember any of this. I don't know how your mind works. I can't teach you how to think. All I can do is give you opportunities to do it. That's all that I can do. Give you opportunities to think about stuff. That's all we ever do. I don't even want to tell you what to think. You don't have to view things the same way that I do. You're not going to view things the same way I do. Not because I'm smarter than you. Everybody in this room is going to be smarter than me. I can tell because y'all look like you're in your 20s. Some of you not even in your 20s. And I'm in my 50s. It just doesn't work as well. Like some people ask me, hey, Leach, you ever going to go back and get your PhD? And I'm like, oh, hell no. First of all, that's a lot of work. Second of all, it's a lot of work for no money. And third of all, there's no way I could compete anymore. Not that it's a competition, but I would just be relying on all of my younger colleagues to try to pull me through because my brain just doesn't work the same way anymore. You know what I mean? Anyway, all we're trying to do is take the stuff that we knew before and adapt it to this new environment. We're just trying to upgrade just by one dimension. We're still working with functions. Notice that the linear function I gave you is that variation on point slope. It's still in that function form because you start off by keeping things small. Dealing with functions is the easier way to do it. How's everybody, okay? I realized today I wore an advertisement. I wore my Godzilla Fest shirt. It just recently happened, but look for Godzilla Fest next year at the Balboa Theater. So they do it every year. Start checking around about August. It's the Balboa Theater up in San Francisco on Balboa. Is anybody familiar with it? If you're not, you should be. After the Godzilla Fest weekend, they showed John Carpenter's The Thing in 35 millimeter. So I happened to miss that because it was on a Monday. But I mean, and the popcorn's really good. And they serve beer. That might be, I'm sure that's not the primary reason. Anyway. So what we want to do is take what we know and we want to start adapting things. That's kind of all we ever do. We could make young people's lives so much easier if we just told them that all that arithmetic that when they get to algebra class, You're just doing that arithmetic over again. Algebra is just arithmetic. You already knew how to do algebra when you started the class. In case you're wondering why your teacher did not mention that, they might not have known. Because that's how teaching works in the United States. So let's grab a surface. Let's grab a curve that we're familiar with, and we know how it adapts, right? So let's grab ourselves, recall, a circle. You know what? I don't want to use a unit circle. I want to bring in the radius. That was the debate that I was having while I was talking about other stuff just now. Like, oh, unit circle and modify or radius and modify. Then I made a decision, wrote it down, immediately changed my mind. Why did I have so much discussion? It's like when you're playing D&D and you're trying to figure out what the modifiers are. The more you have a discussion, the more likely you're just going to fail the roll anyway. Because I go, oh, hang on a second. But is that 3/4 cover? Yeah, 3/4 cover is a +5 to AC, right? So +5 to AC, so it's going to add 5. It's like, oh, but I do have disadvantage on this shot because I'm lying on the ground and I forgot to stand up. And so it's like, oh, hang on a second. Should it matter? Should you, since you already declared your shot? And then you have this big discussion, right, with the DM. It's like, well, hang on a second. You finally decide what to do. You're either going to crit or you're going to fumble. Those are the only two things that happen when you have a long discussion about how the rules work. It's like, okay, we've got it settled out. Roll your attack. 1. It never mattered. So we got a circle of radius r, and what we've done so far is upgrade this to a sphere of radius r. By doing the same form in the equation, x squared plus y squared equals r squared, x squared plus y squared plus z squared equals r squared, which is included it in the same way. We just want to grab some more things that we can recognize. Does anybody remember the equation for an ellipse, a squashed circle? It's a modification of our equation of a circle. The thing about a circle, instead of thinking of an ellipse as a squashed circle, think about a circle as a symmetric ellipse. Yes. Yeah, we would just have different coefficients for the x squared and the y squared. Here's the way it usually shakes out. Usually we would list the coefficients in kind of a strange way. X squared over a squared plus y squared over b squared is equal to 1. Here's our equation for an ellipse. We usually do circle first and ellipse second, but it'd make more sense to do ellipse first and say, hey, circle is just an ellipse where a and b are the same. is if I can rewrite my equation of a circle as x squared over r squared plus y squared over r squared equals 1. So it's just an ellipse where a and b are the same. From a structural standpoint, it makes more sense to do this. But most people know what a circle is way before they know what an ellipse is. So it would make no sense at all to try to teach ellipses before you teach circles. That's how you can identify the most pedantic person in the room. We should do ellipses first, because circles are just like a special case of ellipses. And we'd be like, oh, you are a very strange person. All these kids, I bet their kids are running around just calling them symmetric ellipses or something. So if we just divide through by the r squared, then I get that form of ellipse where a and b are the same. So an ellipse is like having a circle with 2 radii. So instead of plus and minus r all the way around, in the x direction, we're going to have plus and minus a, and in the y direction, we'll have plus and minus b. So we get this squashed circle. We have plus and minus a on the x-axis, plus and minus b on the y-axis. And you can see if I make a and b the same, that's just going to give us a circle. So there should be a 3-dimensional version of this. And we're going to build it the same way that we built our equation for a sphere. This is how math is so predictable. What's the next term I'm going to write? I was actually going to use F, but C is even better. C is even better. So yeah, I'm going to take your suggestion. Z squared over C squared. Not a great choice, because in America, Z and C rhyme, but that's all right. I'll go with your suggestion. A similar thing is going to happen. Notice that this is still the same kind of variation as a sphere with a radius of r. If I take my sphere equation and divide by r squared to put a 1 on this side, the 1 is the thing that helps. If I put a 1 on this side, it's x squared over r squared, y squared over r squared, z squared over r squared. In the x plus or minus r, in the in the x plus or minus r, in the y plus or minus r, in the z plus or minus r. For our ellipsoid, we do the same thing what we did with our ellipse. Plus or minus a in the x direction, plus or minus b in the y direction, plus or minus c in the z direction. Is everybody okay? Now we're just taking the equation, start changing things around a little bit. For hyperbola, we're going to look at the sphere and the ellipse. Well, sphere is just kind of an ellipse. We're going to look at our, sorry, not a sphere, circle. We're going to look at our ellipse and say, well, the x squared and the y squared, they're both positive. What happens if I make one of those things negative? So we get a hyperbola if one of those terms is negative, but structurally, so if I make the x term negative, I'll get one kind of hyperbola. If I make the y term negative, I get another shape of hyperbola. Just a big game of what if we did this? These names clearly came out after we had talked about spheres and circles and stuff like that. So we have circle and we've got sphere. Then we have ellipse. But when we upgraded our ellipses, not ellipses, our ellipses, ellipsi, ellipses. We went with ellipsoid. So make a 3D version with an oid on the end of it. Hyperbola, hyperboloid. Right? Flat Stanley, Stanleyoid. That's how that works. Hyperboloids are going to come in two varieties. Notice I didn't draw them. I didn't draw a hyperbola and I didn't draw a hyperboloid for reasons. To draw an ellipse, it's easy. I just try to draw a circle. It comes out all squashed and it's an ellipse anyway. Hyperboloids, the hyperbolas look very different. Hyperboloids come in two different varieties. We can have a hyperboloid in one sheet. Or we can have a hyperboloid in two sheets. So hyperboloids come in two varieties. Note that to get the hyperbola, it's kind of like we took the ellipse equation and made one of the terms negative. There are two terms, we made one of those terms negative. Some negative, some positive, that's what's producing our hyperbola. I just described that there are hyperboloids in one sheet and hyperboloids in two sheets. And we've got three terms. What do you think produces a hyperboloid in one sheet? What's that? One of them is negative. What do you think produces a hyperboloid in two sheets? I told you that Calc 3 was the easiest of the calculuses. Look how predictable this shit is. If there's one of them that's negative, you're going to have hyperboloid in one sheet. If there's two of them that's negative, you're going to have hyperboloid in two sheets. Because we've been talking about these three conic sections, we should bring up our favorite conic section, the second conic section that we learn about. So, if we take, instead of having x squared and y squared, if we just drop one of them down to degree 1, then we end up with a parabola. Some of you may have noticed that secretly today clearly was about conic sections, mostly because conic sections is usually the first sacrifice that's made in algebra and pre-calculus classes. Pre-calculus is just another algebra class. We just wanted to call it something else because you've already been through elementary algebra and intermediate algebra. So we're like, oh, we can't call it advanced algebra. So let's call it something more hopeful, more aspirational, pre-calculus. Meanwhile, everything that you did before calculus is a pre-calculus class. Way back when you were a child learning arithmetic, that was pre-calculus. If we just started doing that, I think we'd get more people to take calculus. Because, well, if this is pre-calculus, that means eventually I'm going to be taking calculus. And then like 12 years later, it's like, oh, well, here I am in calculus. And it's like a foregone conclusion. Instead of some weird thing that some people do, all those nerds do, taking their calculus classes and working out their calculus at the STEM center and stuff. But secretly today was about conic sections, because that's usually gets passed over. If you were like watching this happen today and you're like, oh, he's talking about conic sections today, that seems kind of from the past, but that's okay. Then good, then you've learned about conic sections in the past. But some of you are like, oh, conic what now? Actually, no. The weird word is conic. So you'd be like, oh, what sections? You mean like Harry Connick Jr. has like a rhythm section, brass section? No. Conic, as in cone. They're conic sections because parabolas, hyperbolas, circles, and ellipses are all sections of a cone. So imagine a cone. And its mirror. Imagine a cone, not just a cone going up, but a cone going down as well. depending on how we cut a plane through that cone, the intersection will produce one of these conic sections. So if I take a plane, if I have this cone and I cut a plane parallel, so let's put this point at the origin because that's an easy place to put it. And let's put this one cone above in the Z and the other one below in the negative Z. If I grab a plane and slice parallel to the XY plane, it's going to cut that cone into a circle. Now, if I take that plane and angle it up a little bit, no longer a circle, we have an ellipse. If I angle that plane up a little bit more, I'm not flexible enough to do that. If I angle that plane up so that that plane is parallel to one of these sides of the cone, I'm going to get a parabola. It's only going to cut through into a parabola. And if I keep angling that plane, eventually it's going to cut the top and bottom of the cones, and that's your hyperbola. So we're just taking a plane and intersecting it with that cone. Circle, ellipse, parabola, hyperbola. Now there are certain places that we can cut the cone where we get what we refer to as degenerate sections. So like if I take that plane and cut it through the point where the two cones meet, then all we get is a point. It's not a circle, an ellipse. No matter how much I angle that plane in between the cone, it's just always going to be that point. So it's like a degenerate circle or a degenerate ellipse, which seems a little bit harsh. But I don't know. I wasn't around when we decided on that word. So, I mean, it seems kind of a dick move on their part, but this is what we got. Also, if I take that plane and angle it through the origin, right, through where the cones meet, and angle it so that it's just touching along the sides, all we're going to get is a line, because that plane will be tangent to the round part of the cone. Any questions? We want to be familiar with these structures because we have talked in a couple days ago about circular paraboloids. And now I get to ask about what an elliptical paraboloid might look like.
I got a question.
Yes, question?
Yeah. Is it possible to see these transformations graphically?
I can't draw them because the aforementioned lack of skill, but I'm gonna call upon my colleague, Dr. Internet, and you want to check out Conic Sections. I'll try to find some good animations.
Cool, thanks.
But if you check out Conic Sections, just Google it. Then sorry, I get distracted every time I use Google as a verb, because Zoom is now also used as a verb, and I don't think it's earned it. It's not been around long enough. I mean, like Googling, that's a verb. Everybody understands that one. I was like, oh yeah, you could just zoom into class. It's like, no, I'm not sure that we can put the brand name on that activity yet. So maybe I should unbrand. So do an internet search for Conic Sections. You'll find some good illustrations. I haven't found a good animation where there's a plane cutting through a cone as a circle, and then you watch the plane just tilt and get all the different Conic sections. I know that means I should just make one or commission one, but what we want to do is still the same thing. Take the stuff that we're familiar with, or maybe kind of remember from our past, or are just becoming newly familiar with, and adapt it to 3 variables. What's this going to look like in 3 variables? Because once we can do that, we can keep going. What if I had, here we have x squared plus y squared plus z squared equals r squared. That's a sphere. That's a 3-dimensional sphere. Specifically, it's the surface. If I want the solid sphere, I have to say, less than or equal to r squared, because that'll get all the stuff inside. But there's that sphere of radius r. So if I have x squared plus y squared plus z squared plus w squared equals r squared, it's going to be the same thing. A four-dimensional sphere, just the shell of it. That one's hard to picture because it's really hard to imagine 4 dimensions, 4 spatial dimensions. It's easy when I have x and then the y and then the z. Now I got to put this w axis in a direction that I haven't used. And now if we flash back to linear algebra, if I pick this direction, that's no good because that's just a combination of x, y, and z. If I make it flat, that's just a combination of x and y. If I make it this on this wall over here, that's just a combination of x and z. I can't just use linear combinations to make a new direction. I need a new direction. How's everybody okay? This is a difficult thing about math. It happens all at once, but we only get to look at it in pieces at a time. Like imagining a four-dimensional object. It's there all at once, but we only get to look at it in pieces. We have to exploit our movement through time picture. All right, so today was about conic sections. I know it was a lot of me talking about stuff and trying to remind you of things that might not be reminders, might be introductions. I mean, that happens too. You meet a colleague or something like that. Have I met this person before? They're probably thinking the same thing. It's like, oh, good to see you, or nice to meet you. What do I say? Anyway, that's it for today. That's it for this week. I'll see y'all on Monday. Everybody have a good day, and thanks for playing.